Hello, my name is Kyle McCleary. I'm a PhD candidate at Carnegie Mellon University, and in this video, I'll present our work on visual inertial navigation for satellites, or VINSat for short. It is, to the best of our knowledge, the first solution to the lost in space problem that relies on only an onboard inertial measurement unit and monocular camera. The lost in space problem is where a satellite needs to infer its position and velocity using only onboard computing and sensing. VINSat eliminates the need for GPS receivers and ground-based radar, providing orbit determination with a standalone onboard system. First, I'll describe nanosatellites, the lost in space problem, the motivation, and a high-level description of our solution. Next, I'll describe why current methods are unsuitable for the rapid proliferation of nanosatellites. After that, I'll cover the design of the VINSat system in more detail, and finally, I will go over the evaluation of VINSat. Nanosatellites, such as CubeSats and PocketCubes, have been deployed in rapidly increasing numbers in recent years. They're compact, cost-effective satellites that have opened up new possibilities for space research, technology testing, and educational initiatives. Current methods for orbit determination of these satellites have significant limitations that I'll discuss in further detail later. Due to these limitations, a significant portion of CubeSats remain unidentified even 250 days after launch, as shown by this chart from the European Space Agency. Because of this, nanosatellites would greatly benefit from a solution to the lost in space problem. Enter VINSat, the comprehensive solution to this problem that can determine a satellite's position with kilometer-level accuracy within a few hours using only a low-cost camera, IMU, and onboard processing. The focus for this iteration is on a nadir-pointing satellite with attitude control due to the limited availability of off-nadir data. Now I'll briefly discuss other methods for satellite orbit determination. GPS receivers are the de facto standard for precise OD, but are often not used in small satellites due to their size and cost. Typical GPS receivers that you might use on the ground or on an unmanned aerial vehicle will not function in space as they're restricted to low speeds and altitudes due to governmental regulations. The receivers that do function in space cost upwards of $5,000, and even more if you want an integrated OD and GPS receiver system. Both ground radar and radio ranging from a ground station can take weeks to months to uniquely identify a satellite. These techniques also require significant infrastructure. Next, I'll discuss the architecture of the VINSat system. VINSat estimates the orbit of the satellite from monocular camera images and IMU measurements. It is capable of determining a satellite's orbit to kilometer-level accuracy in just a few hours. This block diagram gives an overview of the VINSat system and shows the two main components that define it: the vision pipeline and the state estimator. The vision pipeline has two stages. The first stage, region classification, takes in the full-size captured image, reduces it, and classifies the image into 0 or more regions of interest. RC is performed using an EfficientNet B0-based image classification network. The regions of interest are defined by the Military Grid Reference System and were selected by performing cross-correlation-based saliency analysis on NASA Blue Marble imagery. After regions of interest are found in a captured image, the full-sized image is passed to the corresponding individual landmark detection networks. Each region has its own YOLO V8 object detection network trained to detect landmarks. Each landmark corresponds to a specific longitude and latitude on the surface of the Earth, and the center point of the detected landmark is used as the pixel location of the longitude and latitude. Landmarks for each region were selected using the static fine-grained saliency approach implemented in OpenCV on NASA Blue Marble imagery. A saliency map for each region is created, and the top 500 most salient boxes are selected sequentially with varying sizes between 5 kilometers and 50 kilometers on each side. The state estimation problem is formatted as a batch nonlinear least squares optimization problem, aiming to minimize the residuals arising from satellite dynamics across consecutive time steps and the discrepancies between projected and observed landmarks in the camera frame. Now I'll cover the evaluation of VINSat and the results. The purpose of this evaluation is to demonstrate the ability of the VINSat system to sufficiently perform OD from typical CubeSat orbits in a reasonable time frame. To do this, we require a large dataset of images captured from a low-cost and wide field of view camera on a satellite orbiting Earth. Unfortunately, such a dataset is not currently available. Because of this, we divide the evaluation into two main components: cross-dataset generalization and simulation. First, cross-dataset generalization. In order to test cross-dataset performance, we train the networks using only Sentinel-2 imagery and test on only Landsat imagery. This allows us to verify the performance of the networks across changes in view, lighting, and color. The first step of the cross-dataset generalization is evaluating the RC network. The RC network achieves high accuracy for all classes, demonstrating that the appropriate regions have high likelihood of being recognized in an image and passed to the correct landmark detection networks. The next step, is to validate the cross-dataset generalization of the LD networks. Each LD network is evaluated by measuring the performance of the network on the test dataset by measuring mean pixel error of the center points of detected landmarks at varying confidence thresholds. An average across all regions is shown in the table. The low pixel error demonstrates the viability of this approach and shows robust generalization to substantial variations in clouds, season, and camera characteristics. Now, for end-to-end simulation. Simulation environment simulates random LEO orbits and typical rideshare inclinations, and simulates images as would be seen by the reference camera using mosaic Landsat 8 imagery, and runs the pipeline on each captured image. This is an example of a simulation made from Landsat imagery. The detected landmarks are shown as red circles. VINSat is able to consistently detect landmarks in non-cloud obscured portions of images. After over 500 simulations, this plot shows that 85% of the simulated satellites reached a position error of less than 5 kilometers in under 4 orbits. One thing to remember is that satellites in low Earth orbit move at a speed of over 7.5 kilometers per second, so 5 kilometers is less than 1 second of position error. Now for conclusions and future work. Notably, VINSat eliminates the need for GPS receivers and ground-based radar for rapid nanosatellite localization with no reliance on ground or space infrastructure. The evaluation pipeline and datasets we developed were all created using openly accessible tools, and we hope their release spurs further research and development in this important emerging field. As for improvements, an easy avenue for improvement is the addition of more regions of interest, allowing for more frequent detections and increasing robustness to cloud coverage and outlier detections. Testing the pipeline on hardware and finally on orbit are natural next steps. VINSat is an efficient, lightweight, low-cost, and fast method for nanosatellite state estimation, and it paves the way for future research efforts using onboard sensing and computation for satellite state estimation. Thank you.